who is going to give a presentation on environmental at risk. Thanks very much. So, can
Hi, can you hear me, Augustine?
yes, can
And you can see my screen as well, right? Can you see my screen?
yes, we can.
Perfect. Okay. Hello, everybody. I am Karn, and I am a third-year PhD student in the School of Geography, Earth, and Environmental Sciences. And today I'm going to present about the results I've obtained during the course of my PhD, which focus on using satellite data to monitor citywide air quality. So before I start, I'd just like to thank all my collaborators and contributors, my supervisors, and especially BERA, because of whom none of the results would have been possible. So firstly, what is the problem? The problem is air pollution. And so I'll take you outside my house in Gurgaon, near New Delhi in India, around 4 years back, where we had a serious pollution episode where almost for a week we couldn't see daylight. And this is a photo which I took around 1:30 p.m. And so that's the bad situation over there. But it's not just me, air pollution affects everybody. Globally, in 2015, 4.2 million people died just because of air pollution. Then 40,000 of whom were just in the UK. In India, 1.2 million people die, which is even more than the population of Birmingham. There is excess mortality estimated in Europe because of the aggravated heart and lung related diseases. There's unsafe air quality at 2,000 sites in the UK where we have surface monitor, but we do not have any idea about the sites where we do not have any monitors. Air pollution is said to be damaging every organ in the human body. It also takes decade of a memory, so you can age your brain by a decade straight away, and it's even been linked to miscarriages. Now, what's common between all these news articles and journal publications? And that's the two main pollutants, particulate matter and nitrogen dioxide. Now, what are they? Particulate matter is nothing but particles suspended in the air. You can have particulate matter PM10, which is particulate matter with size less than 10 microns. It's very small, roughly 1/6. This is the size. This is the human hair, and it's roughly 1/6 the size of human hair. And you can have even smaller particles, PM2.5, with size less than 2.5 microns. Now they're quite small. They can easily enter the human body, lungs, alveoli, and are more harmful. On the other hand, we have nitrogen dioxide, which is a reddish-brown toxic gas, but obviously the ambient concentrations are quite low, so it appears colorless. Now the good news is that in the UK, the emissions have reduced for both particulate matter and nitrogen dioxide. For PM2.5, there have been emissions almost 80%, and for nitrogen oxides, almost 70% in the last 50 years. And according to the UK air quality objectives, the annual mean compliance limit for PM2.5 is 25 microgram per meter cube, and for nitrogen dioxide is 40 microgram per meter cube. The interesting thing is that while we meet the requirements for particulate matter, we do not for nitrogen dioxide. Now, where is this nitrogen dioxide coming from? So here I present pie charts from UK's plan to tackle roadside nitrogen dioxide, where there are different sources like road traffic and background. And we can see that almost the dominant source is road traffic, contributing to 60%. And on the right pie chart, we see the different sources contributing to the local road traffic, where we see that 90% of it is coming from the diesel vehicles. Now, to get these emissions, the question is, how do we know now if the nitrogen dioxide is going down? So there should be some measurements taking place. So if you had a chance to walk between Tesco and Aldi in Selly of Birmingham, you may have observed this gray box. And I don't know if you have or not, but this is one of the air quality monitoring stations that we have in Selly Oak. Similar to that, there are many others in Birmingham. So you can actually look where you reside in Birmingham or have lived in Birmingham or are planning to come to Birmingham, and you can see if there is a more local air quality monitoring station nearby. So if you were somewhere in the university campus, hopefully soon, we also have a new station which was which started its operation last year. Now, this is a map just to show how spatially these air quality monitoring stations are spread, and the colors show that most of these air quality sites show a decreasing trend in nitrogen dioxide, except the one in Moore Street, which is near Birmingham city center, where we see an increase in pollution levels. Now, so I tell you here that we have been doing surface monitoring of air pollutants. Now here we have a map from for London, which is the Greater London boundary, and the data for it is from the London Air Quality Network for 2005, where the different surface monitoring sites show the annual mean nitrogen dioxide level. And I told you earlier that the nitrogen dioxide compliance limit is 40 microns per meter cube. So any color other than dark blue means the levels are beyond compliance. So these surface monitoring networks have their own limitations. Firstly, they're quite expensive to set up and maintain, costing almost £50,000 for each monitor. Then there is limited spatial and temporal coverage. So you saw the map for Birmingham in the previous slide and here for London. So they're not throughout the city. I mean, you can see it for London for 2005, but that's not the situation for all the other cities. And then there's limited temporal coverage as well. We only monitor a limited number of pollutants, especially the ones which are regulated. Nitrogen, we do not regulate ammonia. And so only 3 sites in the whole of UK do continuous monitoring of ammonia. Lastly, there are issues with data quality. So I've had issues with processing data for both UK and India, which I can discuss in detail later on. And the data can be inconsistent. So in this animation that I've created, I showed that sites come and go over time. So this makes it incredibly challenging to obtain a long-term record of the city-wide nitrogen dioxide levels. Now, this is the condition of the most widely monitored pollutant, nitrogen dioxide in London. But we can't comment on the other pollutants as well as for other cities. So what is the solution to this global challenge? And satellites are the answer. So in this time series, I show that the sensors have been in space for over 2 decades for monitoring both gases and particles and providing us with petabytes of data. The red bars show the completed missions and the green bars show the ongoing ones. And the future sensors are going to be even better. They'll be cheaper and will have finer spatial resolution. Now, these space-based instruments provide us with extensive data coverage. Here I show heat maps for both UK and India, and I have averaged out the satellite-based nitrogen dioxide level for 2005 to 2018. So it's 14-year data, where the shades of yellow and orange are showing the high levels of nitrogen dioxide, and the cooler shades show the low levels of nitrogen dioxide. Such maps are helpful to identify the hotspots of nitrogen dioxide pollution. Now, we have developed our approach focusing on 4 dynamic cities, 2 in the UK, 2 in India. So in the UK, we focus on London and Birmingham, which are the top 2 most populous cities. Out of the 40,000 attributed deaths to air pollution, more than 25% are just from these 2 cities alone. In India, we focus on 2 cities in the Indo-Gangetic Plain, Delhi, which is famous as the world's most polluted capital, and Kanpur is a rapidly industrializing city. And in 2016, World Health Organization recorded it as having the highest levels of PM 2.5 in the whole world. Now, I'll take you through a crash course of chemistry just to get everybody some understanding. So the air we breathe is a cocktail of pollutants. You can have oxides of nitrogen dioxide, oxides of sulfur, ammonia, non-methane volatile organic compounds, or NMVOCs, ozone, particulate matter. Now, all of these air pollutants are emitted by multiple sources, can be industrial, agricultural, can be from the domestic combustion, or from the vehicles you generally drive. Now, all of the primary pollutants undergo chemical reactions to form secondary pollutants. Some can be precursors of ozone, which is a gas, a blessing in the higher atmosphere, that is the stratosphere, but is toxic at ground level. And some gases like ammonia, which are not regulated, can contribute to formation of particulate matter. And thus it becomes essential to regulate ammonia emissions as well. Now, all of these collectively impact both human health and food security. Now, satellites are like this eyes in the sky, which are observing this cocktail of pollutants. And so For today's presentation, we are focusing on 3 of the sensors: OMI for nitrogen dioxide and formaldehyde, ERZ for ammonia, and MODIS for PM 2.5. But how do satellites measure air pollution? So I told you the instruments are there on both satellites. Now, the sun is the source of energy. The Earth is receiving the incoming solar radiation from the sun and reflects it back. Now, the satellite is measuring the backscattered light. Now, it's important to note that the satellite is measuring the whole atmospheric column, which can be more than 10 kilometers. But the air pollution is generally at the surface, around 1 to 2 kilometers near the source of the pollution. And the column, the satellite column, is quite sensitive to changes in the surface concentration and can thus see what's exactly happening at the surface. Now, one important thing to keep in mind here is that while the surface monitoring, which we saw initially, observes a mass concentration of a point source, which is measured in mass per unit volume, the satellite, on the other hand, is measuring the whole column, giving you a columnar density. That is the number of molecules which would be there per unit area. Now, before we start using the satellite observations, the first step is to observe if there are any caveats or limitations. So satellites do have 2 limitations. The first one is they're at a coarser spatial resolution. So in that case, we need to sample the whole city. Giving you a brief timeline here. This is a map around London area. And in 1995, European Space Agency launched an instrument, GOM, which had a very coarse resolution. So it used to give 1 pixel, which was 320 kilometer by 40 kilometer. Then things improved. And in 2002, Skiamaki came with a finer resolution. GOM came up with its second mission in 2007 with an even finer resolution. But between these 2 missions of the European Space Agency, there was one mission by NASA which had OMI, which is at a finest spatial resolution possible, and it was launched in 2004, 24 by 13 kilometer. Now, this is a very small pixel, the best spatial resolution we could get. And so this helps us in observing the pollution at the city level. The second thing is that the satellites, they pass overhead once a day. So OMI's overpass time is 1:30 local time. So it will be passing somewhere around an hour from now, right overhead. Now, these satellites are in the low Earth orbit. That means they are 750 kilometers away from the Earth's surface. And so they complete an orbit around the Earth in 90 minutes. So in a day, it takes roughly 14 to 15 orbits. And here in this animation, you see the different snapshots where each snapshot is 1 complete orbit. So it takes roughly 1 day to get the global coverage from satellites. Now, before we use the satellite data, we also conducted validation against the available surface observations to see if satellites are exactly capturing what's happening at the surface. So first, I show here satellite versus surface nitrogen dioxide for London. On the y-axis, we have the satellite-based nitrogen dioxide levels, which we have sampled for the entire Greater London area. And on the x-axis, we have surface nitrogen dioxide levels, which we have sampled around the satellite overpass time to make them comparable. Each of these points here are monthly averages, and the Pearson's correlation coefficient indicates consistency. Like here, the value is 0.51. So it's important to note 0.51 is perfectly fine because here we are comparing a columnar density to a surface concentration or a mass concentration. So it's perfectly fine to have a R value of anything greater than 0.5 is perfectly fine. Here I've excluded winter because the relationship between satellite versus surface nitrogen dioxide is quite complex and is seasonal dependent. We did a similar scatter plot for the winter months and observed similar relationship. But this is for nitrogen dioxide where we had a lot of observations. The story is not the same for the other pollutants. So for ammonia, I told you there were just 3 super sites which are doing continuous monitoring. So we did not get any observations for London. So instead we went 100 kilometers west of London to Harwell and got the surface ammonia concentration from that one site around the satellite overpass time. And on the y-axis, we have the satellite-derived ammonia levels, which are around that Harwell supersite. And we again see that there is a nice correlation between the satellite versus surface ammonia levels, which tells us that satellite ammonia is able to reproduce what's happening right at the surface. Similar analysis was conducted for satellite versus surface PM 2.5. Now, those were nitrogen dioxide, ammonia are gases. So the story is quite different from when we compare particles. Now, aerosol optical depth or AOD is a measure, as it's basically a proxy for PM 2.5, as it measures how much aerosols are there in an air column or atmospheric column. Now, we did compare MODIS AOD with surface PM 2.5, and the correlation R equal to 0.23 is not quite good. And it makes sense because the relationship between AOD and PM 2.5 is quite complex. It depends on a lot of things like aerosol composition, whether it's dry or what's the relative humidity, what are the meteorological factors, and or where is the aerosol in the atmosphere. It could be high up a chimney, for example. So instead, we directly looked into the trends in both surface PM 2.5 and MODIS AOD, and we observed similar values of 3.7% per year for both Birmingham, and similar results were obtained for London. We did not get a good agreement from the monthly means, but when we looked into the time series of the monthly means, we did get a good agreement between the two. Our work is currently in review, and if you are interested, you can have a read through. Now, after doing successful validation, we did trend analysis to the long-term record of these satellite observations. And this is where BERA sources play a major role, because it's a lot of data that we have, and for each pollutant. So here is a time series of satellite-derived nitrogen dioxide levels for London from 2005 to 2018. And this is the trend line, the black is the trend line, and we see a statistically significant declining trend, which tells us that the nitrogen dioxide levels over London have decreased by 35% in these 14 years. This indicates that the policy changes have been effective. Another interesting result that I have here is to show the trend in non-methane volatile organic compounds for London. So overall, it's a similar time series, and the blue dots are the monthly averages. So we do see that the trend is 0.5%, and it was not significant as the p-value is quite high. But the interesting bit is that from 2012 onwards, we could visually see that there is an increase. Now, we inspected this trend, and this is 9.3% per year, and it's quite significant. Now, this increase tells you that the reactive NMVOCs have increased by over 65% in London since 2012. Now, this is something which we have not observed in the emission inventories, and this is quite an interesting result to see what could be contributing to the increase in the NMVOCs. We suspect it could be because of the increase in domestic combustion. It could be the increase in the use of household solvents, as well as the food and beverages industry, as these are the three sectors which have shown an increase in the last 7 years. Now, I won't show you the trends for all, but I have a summary slide to show you the trends for all the cities in the UK and India. So these were the 4 cities we were looking into, and these were the 4 pollutants that we were catering to. And what we see that, so a blue downward facing arrow indicates a decreasing trend, an upward facing arrow shows an increasing trend. The darker shades include the, basically indicate the significance of the trend. So what we see, London and Birmingham are showing decrease for most of the pollutants, except NMVOCs, which have shown a recent increase, 2012 onwards. And for the cities in India, the air quality has been degrading, and so we see an increase. Now, I thought of taking this work to the next level, and so these are just 4 cities that we looked into, but the next frontier in air pollution are the tropics. Currently, we have around 33 megacities in the world, and population has been increasing, and it is estimated, according to a 2016 study, that there will be 51 cities within the tropics by 2100. Just to give you a size of the population, Lagos in Nigeria would have a population of around 80 million, which is roughly, Lagos would have a population of 80 million, which is roughly 6 times the population of present-day London. And Dar es Salaam in Tanzania would have a population of 60 million, which is twice present-day Delhi. So it's going to be a massive boom in the population. Most of these countries do not have air pollution control measures in place, or they are maybe in their starting phase. So this is another reason. And the last reason why tropics are really important is uh, over here. So here I have indicated a map, which I populated yesterday for all the surface sites. So here is all the publicly available data for PM 2.5 surface monitors from the website OpenAQ. So you can, whenever you want to have a look at the data, you can, it's a free source available, gives you data for last 90 days. This is for yesterday. And if we look at the tropics, you hardly see any monitors. So this is an important concern, that there is limited routine monitoring done across the tropics. And so I decided to investigate the 51 megacities, because they are going to be future megacities. And so it's important to take care right in the future and have policies directed towards them. So here are the preliminary results. So first is the OMI nitrogen dioxide trends for all these megacities. Now in this map, you'll see all the 51 megacities. The bubbles are indicating the size of the baseline. So the baseline is the 2005, or the starting date. The smaller bubbles here indicate that, you know, Africa has low levels in 2005 and compared to the ones in Asia. The colors indicate the trend in annual trend in percent per year. So the warmer shades are obviously an increasing trend, and the shades of blue are the decreasing ones. Any significant trend has been outlined. So what we see in this map here, that the nitrogen dioxide levels have increased in 46 out of the 51 cities. And most of them are significant, as you can see from the outline. What contributes to the nitrogen dioxide in these cities are mainly fossil fuel combustion, and then there can be seasonal contribution from the biomass burning. Interesting bit is here, Jakarta in Indonesia, which sees a significant decrease. So we inspected this and we observed that Jakarta came up with the vehicular emission norms in 2005, which has led to a decrease in the nitrogen dioxide levels just for Jakarta. But no other city which sees a decrease has a significant decreasing trend. Next, and two interesting clusters that we see here are for West Africa, where the increase has been around 1 to 5% per year, and it's quite significant, and over India and Bangladesh. These cities have shown an increase from rating like 1% to 14% per year. So that's quite an increase in the nitrogen dioxide level in the last 14 years. So definitely there should be some policies targeting nitrogen dioxide in India and Bangladesh. Then the next trend that we looked was for the trends in formaldehyde, which are representative or proxy for the non-methane volatile organic compounds. And we see that the trends are quite mixed. They show an increase in 37 out of 51 cities, but most of the trends are not significant. Now for formaldehyde, as I mentioned, formaldehyde comes from the industry, solvents, use domestic combustion. There can be some biogenic sources like trees, like the oak and pine trees. And there can be some seasonal contribution from biomass burning, which happens a lot in Africa and the Indian subcontinent. So these are the net trends that we have. And as a next step, I will be trying to tease out what is the contribution from the biomass burning, so we can attribute them to the anthropogenic or the human activities. The next trend, which is a work in progress, is for particulate matter or the MODIS AOD levels. So I've obtained it for 33 cities, and we see that from those 33, AOD has increased in 25 of the cities. Two interesting clusters are again over India and Bangladesh, where we see 3 to 8% per year. So it's quite significant. The baseline was also large, and you can see that significant trend. So PM 2.5 levels have been really increasing over the Indian subcontinent. But the same is not over Western Africa, where we did see an increase in the nitrogen dioxide levels, but not for PM 2.5. The trends are not, none of the trends were significant. So that's quite an interesting result. And as a next step, I'll be looking into what is driving those results. For PM 2.5, because it's already it comes from secondary sources like nitrogen oxides, ammonia, and non-methane volatile organic compounds, as well as primary particles can come from dust, especially Saharan dust, crop and trash burning, which takes place a lot in northern India. There can be residential fires, open fires, or even the charcoal that you burn for summer barbecues. So all of these are contributing to PM 2.5 levels. But just to give you a flavor of what's happening currently, I hope you do remember me presenting the slides of the time series of the different sensors. So in 2017, there was a high spatial resolution space-based satellite sensor, tropomy, which was launched um, by the European Space Agency. And this has the finest spatial resolution ever, which is 5.5 by 3.5 kilometer. So this helps us to investigate the smaller cities or sub-city level pollution in case of cities like London. Just to give you a teaser, here I've created a map from tropomy for, just give me a second, for October 2019. If you have been observing news around March or April, this map would look familiar. So this is a map for October 2019, and this is using tropomy nitrogen dioxide levels. And you can easily see the pollution hotspots. Like this is the Po Valley, Northern Italy. All the cities emerge as hotspots. You can see all the major cities like Madrid here, and a lot of pollution plume over the UK. Now, if we further deep dive into the UK, we can actually see, now this is just for 1 month, integrating it with the wind data, we could see that there was a strong southerly wind. So there's a wind from the south, which is pushing this plume of pollution away right into the north. So you can actually see how much of pollution is coming from continental Europe right into the UK. And if you want, you can either further deep dive right into London and even see how the pollution levels can differ between a weekday and a weekend. So that's quite interesting. And this is it just for 1 month. And this is, so one orbit has a data size of 450 MB and roughly 15 orbits a day, and getting the data for 1 year is around 2.5 terabytes for one pollutant. So it's a lot of data, and this is where I feel it's been really essential to have bare resources, process my data, download it in the research data store, as well as process it using BlueBear. Otherwise, it wouldn't have been possible. And you may have seen similar maps to assess the impact of lockdown, where a lot of the studies over China and over Europe showed a big plume over Po Valley in Italy. And then during lockdown, there was nothing. So this is where tropomy has been in the news, and it's the present. Just to conclude my work, 3 key points is that you can actually use satellite observations. They provide you long-term, consistent global coverage of air pollutants. So you can get it, especially in places which lack surface monitoring capability. From my first project results, we did see that the air quality related policies have been effective in the UK, but there was no evidence observed still for India, not for the 2 cities that we looked into. And for the future tropical megacities, the megacities of 2100, we did see that there have been increases, and quite significant increases, in these short-lived air pollutants. As next steps, I still have to complete that analysis because I'm limited by the 3 terabyte size of the RDS, and then interpret the drivers of these trends. What are the different sources? Try to tease out the biomass burning contribution, as well as compare these trends that I'm observing from satellite to the trends which I would get from global emission inventories, because these are the emission inventories which go into Earth system models, and they predict whether how the changes in weather, especially global climate change, and all these different things. So thank you so much for your attention, and I'm happy to take any questions.
Thank you so much, Ken, and for such wonderful and interesting presentation. And it's so interesting how your research span across continents, and the visual representation has been so lovely. So we welcome question and answer from the participants. You can just post that into the chat room. But in the meantime, while the participants are posting their questions, just like to read if we have something.
I believe there's a question from Debbie, and
there's a said from a very interesting can. Which software do you use to process your data on BlueBear? That's from
yeah. So thanks, Debbie. And so as of now, I have been using R, and now I'll be moving on to Python as I process, because it's the data size is increased as I move from OMI to tropomy. So yeah, the move will be to Python. I really like the idea of having those interactive apps, as they have helped me to debug my codes before I put them using command line.
Okay. And Ken, I would like to ask some of the geospatial analysis that you
Right.
have done. There are continents or some parts of the world, like when you talk about that, the network is not yet done in such a way that you can use software to actually get the data. So if you, don't you think that when you start comparing and looking at where or which of the data you collect, when you collect limited data for a particular region, you're going to have a report of saying this has not been done to a great extent there, and that's applicable to some part of Africa that I know that the connection, if you want to get geospatial data with software, it will be very hard because the structure, the infrastructure is not there. So how do you actually attempt or resolve that in your research?
Uh, so, Augustine, thanks for your question. I'm not very sure if I understood that correctly. Just to give you a teaser, so what exactly was happening, there is problem with the surface data that we have, but the satellites can observe everything. So if you remember the maps which I had for UK and India, so you can actually observe it in all the places, irrespective of what's happening. Obviously, there are some caveats, like you may have clouds and you may then not, like for UK, data quality is an issue even from the satellites, because you have clouds most of the time, and then the satellites just can't observe what's happening at the ground. But in case of Africa, yes, I think it was easy to get most of the data. The problem was around the Sahara Desert, where the dust creates an issue. So in those cases, yes, we do have caveats, but the way I have processed it is so obviously you can't, sometimes there are instances where you cannot get data for all 31 days of the month, or let's say 30 days of the month, or 28 for Feb. In those cases, I have kept a threshold that if we have data for more than 5 days in a month, we consider it representative of the month. So even if you have data for 5 days, I think it's a good number to come up with, derive with the monthly mean of the tropospheric column of the pollutant.
Okay, that's um, that's interesting. So let's see. Well, we have another question or comments here. Very interesting information. Can see the visualization of pollutants over time and space using local and satellite data. How can you get to root cause and differentiate between sources, each industry versus traffic or versus agricultural versus domestic pollution for highly polluted region? That's a question from David March.
Perfect.
Can?
Yeah, thanks, David, for that question. So that's a very good question, and that is the next step. So the step one is basically just to observe how you're getting the data and everything, and the step two is to integrate the data that we're getting from both local as well as satellite data with a chemical transport model, where we feed all this data. It does a lot of data assimilation, and the end result is and you also use the emission inventory data that we have to actually be able to quantify how much, or basically apportion the different like apportion to the different sources, like how much of it is industrial or versus traffic. So that the next step is basically to use a model. Yeah.
That's great. That's interesting one. We're still waiting more questions, and I just looking at the as we're waiting those questions, looking at your research, which is so interesting, and what do you feel that the output will be beneficial globally with regards to the Earth and also a response to pollution and environmental hazard precautions?
So the most important thing here from my work is to observe what are the long-term trends. And the reason I have taken this work is to understand if there have been any recent policy which have been introduced in different parts of the world. And there you can actually observe whether these policies are being effective or not. So this tells you and two things: whether the policies are being effective or not, and if the pollutant levels are still increasing and they are quite significant, then it tells the government, the policy makers, as well as the stakeholders to address the pollutants which are increasing and in which parts of the world. Because the interesting bit is, different countries are at different stages of development, right? So every country has its own interesting story. Every country has its own source of pollution, so it's all different. So every country needs to be taken. The pollution issues should be addressed in a very different way. So a study like this basically helps just to give a flavor of what's happening there. And the next step is for the stakeholders to see which pollutants were they targeting. Was it the right pollutants that were being targeted, or do they need to change their priorities? Because satellite observations, the good thing about satellite observations is the bottom up emission inventories, which is there currently in the UK, for example, it takes roughly 2 to 3 years to get access to the data. And using satellite data, you can easily get it like access to yesterday's data, for example. So it's quite fast. So you just need to have like high performance computing systems to get access to the data set
Brilliant, Karn.
and observe whether the pollution is coming down or not.
That's great. And there's an interesting question from Lizzie Jabo. She asks, very interesting presentation. Exposure to pollution is increasingly used to study health outcomes, educational outcomes, behavioral issues. And she now asks, how is exposure to pollution measured? Average in a month, number of days of high pollution,
Okay, thanks, Lisa. That's a very nice question. So this is a question which is targeted most to people in public health. So I am just measuring what's the concentration. And so you have emissions of pollutants from the source. These emissions are basically concentrations which are there existing in the environment, but the concentration is not the same thing which we are inhaling or taking from through the surface of our skin. So the concentration to exposure is another story, and that's quite different. And so a lot of health studies need to be done and those studies are done for different age groups, different population, and just to understand how much is the exposure from the concentration that I have measured. Yeah. So I won't be able to directly comment on how the exposure is, whether it's an average in a month or the number of days of high pollution. Yeah.
Yeah, and I think she's also interested in knowing, the way you are doing your measurements because, how say, and do you have a range of time? Because that's what I can get from the question. Do you have a range of time, and how do you do the measurements? And I think that's the interest in the question.
Yeah. So if I understand the question correctly, when we look at the range of time, so the reason why we looked into 2005 to 2018 was because the finest spatial resolution from OMI was launched in 2005. And so that was the longest record we could get. And the second thing is to see whether these satellite measurements are doing a fab job or not. We only when I was showing the validation results, we picked up observations for those days only where we had both surface as well as satellite data. And that is how I'm doing an average in a month. So from there, I'm getting a monthly mean. And those were the monthly means of satellite, which I was comparing against the surface. In this case, number of days of high pollution would not be there because the different countries have different ranges. So first we need to agree what is the threshold. In my case, we were just looking at the monthly mean. So I did not look into the number of days of high pollution because we need to define then what is the benchmark or what is the baseline where I want to say that if PM levels are greater than, let's say, 100 microns, is it high pollution? That may be high pollution for UK, but that is, that may not be the same thing for, let's say, India, because in most of the days you have pollution levels which are 100 microns per meter cube. If that is the story, then obviously in India we have pollution, high pollution for 350 days.
That's true.
Yeah.
Thank you so much, Ken. And there's another question coming in from Dave Owen. Could a new smaller resolution be used to measure pollutants from the large supertanker or cargo ships, or a new thing, or any new things given the drastic reduction in size?
Oh, that is a fantastic question, Dave. I'll try to share my screen again to be able to answer that. I think I forgot to mention one of the things, which is in this last slide, because of the high spatial resolution, you can not only see the cities, but you can also see the shipping tracks. So you can actually see all these shipping tracks in the Mediterranean from Spain and Portugal all the way to the UK and Ireland. So this is quite interesting. This is something which has not been done before. There are quite many applications of tropomy. So this is one application which I'm sharing right now. There have been many other interesting results, studies done, where they have even looked into the the natural gas pipeline in north of Siberia. So that is something which is quite an interesting application, I would say. So it's not just with the air pollution directly, but yeah, you can observe the shipping tracks, you can get emissions from the shipping tracks, because this is a source which I think currently has had a lot of high uncertainty. And having such a high resolution instrument is definitely a win-win.